All right, time for us to get started. Announcements.
Yeah.
So yesterday kind of sucked, as you all know, with the technology not really working and having to lose. Yes, I actually wrote an announcement for classes.
We'll see all you there. Half people failed last time.
Yeah.
I'm just kidding, last time. It's the truth, guys. I'd rather not have you have to retake that again. 5 hours.
Wait, you're talking about tomorrow, right?
What? Tomorrow, 2:16. Over there.
Yeah.
I'll be taking attendance.
What are you gonna do?
No,
Yeah. So ACM is hosting 8 study sessions this Wednesday, tomorrow, and next Wednesday, 2:30 and 2:16. Highly recommend those of you who are taking the 8th to go spend some time there, study. I'm gonna try to make it as well. I think I should be able to. So it'll be a good place to go practice 8-related problems.
You know what we're gonna be doing, like the practice aid from.
So I believe so, going through practice 8 problems. And I can generate quite a few problems that aren't exactly those practice problems off the top of my head. People can talk about what do you feel like you are weaker at or haven't studied as well. One thing that I'm planning to do in 212 this Friday is a problem that at least has you reading from a file and printing to a file. So we can start using print stream a little bit, since I don't know if you've done that since 211, might have been a little while. So trying to get some experience with that there, as well as probably do that in the 8 study sessions as well. We completely lost yesterday's recording, was the announcement I was starting to make. So I know yesterday was kind of an important day, and I apologize to Chris remotely because I was not able to record what happened on the board. So Chris, if you'd like me to go over that, I'd be happy to. Just let me know and I can leave you in during office hours. I'll have to go over that. For everybody else, I apologize. There's no recording of what happened. I am always happy to go over that material during office hours, but we're back working today in our usual classroom technology that actually functions. So we should be back to normal for today. So we've gone through a couple days of recursion practice now. It seems like the class as a whole is feeling pretty mid about recursion, which means that we need some more practice. This is good because I have 2 more algorithms that I want us to implement recursively before we move on. So the next couple days are going to be introducing that and getting a bit more practice with recursive thinking. I also need to figure out what I want to assign you on it. I would like to have that to you by tomorrow, so that you have a week to work on it before it will be due next Wednesday, which I'm hoping will be enough time to get you feedback before you take the 8th next Friday. Questions about anything related to course content, timing? Anything else that's going on? Yeah.
so, the 8 practice. Not the practice test, or whatever the workshop.
Yeah.
How long is that?
That's a good question. I don't know how long it will go on. I would assume as long as there is interest and there's someone willing to lead it. It doesn't necessarily have to be the people who said they were going to lead it. It could just be they have to leave. Someone else steps up and takes that leadership role. So I would assume that as long as people want to be there, then there will be someone willing to lead something. So if you can't quite make it at 2:30, I would still show up at some point, and hopefully there's still people doing something. Good question though. Anyone else? All right, last time we reversed a list, and I believe we basically finished this off. I didn't write a driver for it. I can quickly write a driver for it before I upload the code, but I believe we tested it and it worked. Is that right? All right, so I'm not going to spend too much more time on reversing the list unless people would like to. I can always come back to this at any point for studying, but I would like to get us to the new practice stuff. So I am going to start out by talking a little bit more about what else we can do with recursion before we go into the other practice problems. So we'll have a little bit of a lecture and then we'll end today's class with the next practice problem. So first thing I want to talk about is the difference between iteration and recursion. Is there really a difference in the power of these? So iteration is what you do when you write a loop. Recursion is what you do when you write a method that calls itself. And it turns out that they solve the same subset of problems. Anything that we can write iteratively with loops, we can also write recursively. Anything that we can write recursively, we can also write with a loop. And I think I mentioned this before, but sometimes a problem that is difficult in one way is significantly easier in the other, which is why we bother to learn both tools. There's also an entire class of programming language called the functional programming language that straight up does not support iteration. It has to emulate iteration through recursion. So even though it has a while command, what's going on underneath the hood is recursion. All of those things. There is also one downside to recursion that we need to talk about, because it's something that becomes a very large problem if you write something recursively. And that is the stack overflow exception that can occur. Have we talked about the stack overflow exception in here? I forget. Not really. So every time a recursive function is called, it goes on what we call the call stack. And the call stack is a place of really fast access memory that allows us quick access to things like the variables that are within the scope of that function. So when you, in a method, declare int x equals 5, we want really fast access to the question, what is x? So each of these functions takes up some amount of space on the call stack, and we have a very limited amount of space to work with. And it turns out that once we have about 40 functions on the call stack, we run out of space. Because for all intents and purposes, we shouldn't need more than 40 paused and running methods. When we were walking through the reversal list function yesterday, and we saw that we paused at a particular line and came back to it, that function needs to be stored in memory somewhere. What line we are currently on, what the variables are, what the current values of those are. They're not in the current scope, but they need to be stored somewhere so that when we come back to it, we have access to it again. How do we do that? Well, we just store it in the call stack. It's just not the active function in the call stack. So as we start to use more and more of this, going into a larger and larger recursive depth, we start running out of space. If we run out of space, we get what is called a stack overflow exception, which means we tried to recurse, but we were unable to recurse because we didn't have the space to store the new function call. Does that make sense? So it turns out Java does not even support tail recursion, but I'm going to go over it because if you're going to be thinking recursively, it's important to know how to just like it's important to know how to write an algorithm efficiently, it's important to know how to write a recursive function efficiently, because tail recursion will allow you to bypass the call stack, basically, where you don't need to store the function on the call stack because you don't actually need to come back to it. So I get in moods when I write slides. So anytime we can write a function recursively, we can also write it tail recursively. And tail recursion just says when we make the recursive call, it is the last thing that we do. And that means that there's nothing to come back to. So it works more like a loop, where when you finish the recursive call, there's nothing that we need to store for later. If we don't need to store it for later, we can delete the function off the call stack. Which means that we can get to a recursive depth of more than 40 because we don't have to come back to it. So there's no logic to return to. Thus, we don't need to keep the function on the call stack. And that means in practice, what we end up needing to do is keeping track of the running total or the running cumulative something that we are doing in the way that we would do it in a loop. So if we think about the difference between the iterative factorial and the recursive factorial, in the iterative, we kept track of a product that represented the product calculated so far, as we did something like 5 times 4, that's 20, times 3, that's 60, times 2, that's 120, times 1, that's still 120, all right, we're done. Could we model that line of thinking recursively? And the answer is yes, but not just with a single parameter like the way that we implemented it. We need an additional parameter that keeps track of that product, that same variable that we were using iteratively. So when you pass in the parameters, you would pass in something like 5, 1, where the 5 represented the number of the factorial we want to take, and the 1 represented the product so far. The next call would be 4, 5, where we took the 1 times 5 and the 5 minus 1. So now we want to calculate 4 factorial and multiply it by 5, the second parameter that we're passing in. Let's actually take a look at it. So here is the tail recursive factorial that has those 2 parameters. It has the current value that we're taking the factorial of and the product calculated so far. Before, we had a base case that said if the factorial was less than or equal to 1, return 1. And then we ended up calculating the product on the way back up the recursive chain. So we did 1 times 2 times 3 times 4 times 5, and we backed up the recursive chain. Now, when we hit the base case, we are done. We've fully calculated it. The variable product is going to hold the answer by the time we hit the base case. So before, if we were kind of modeling this visually, we had 5, 4, 3, 2, 1. We returned 1, and then we multiplied it by 2. The total thing so far, we're like times 2, times 3, times 4, times 5, and then we output 120. So we went down the recursive chain, hit the base case, stored each of these values, and on the way back up, we multiplied. And now we're saying we're going to pass 2 things down the recursive chain. So we're going to start with 5 and 1. We're going to pass down. We're going to multiply the 5 by 1 as we go. So product times current. These are our 2 values. 5 minus 1 is 4. 1 times 5 is 5. Now we pass that down the recursive chain. 4 minus 1 is 3. 5 times 4 is 20. Passing that down the recursive chain. 3 minus 1 is 2. 20 times 3, I guess, is 60. And then we pass down 1 and multiply the 60 by 2 and get 120. By the time we hit this 1, we hit this if statement, and we take this value and we output it. So we do not need to go back up the recursive chain for any reason, which means that we don't need to store any of these function calls on the call stack. All of the information that we need is being passed on, just like it was iteratively in a loop. So tail recursion is not going to be super necessary or useful in this class because Java doesn't support it. But in the future, if you ever work with a functional language, it is always worth thinking about and writing recursive functions, tail recursively, because then you can actually do things with more than 40 recursive depth. That becomes a really big limitation because recursively we do a lot with lists. And a lot of the lists that we deal with out in the world are longer than 40 elements long. If you want to support something that's more than 40 elements long, the way that you implement your recursion needs to be tail recursive. Does that distinction make sense? Can anyone think of any cons associated with implementing it this way? There's one really big issue with fifth tail recursive function. And it has to do with usability. It's absolutely correct.
You could put some random value in for the product when you're calling it the first time.
Yeah,
Break it.
absolutely. Think about this from the client's perspective. You write this and you publish it. You're not going to be the person who uses it. Someone else is going to use it. In order for this to work like you intend, people need to know to pass in 1 for this initial product. If they don't pass in 1 for this initial product, then it's not going to do what it's supposed to. If they try to use it with a single, like, when we think of the factorial of 5, we don't think of there being a second necessary parameter associated with that. Can anyone think of what we could do about that? How could we fix that?
You just make that one private and then you have a public one that just takes the first one,
Yes,
calls it over.
that's exactly right. Does that make sense to people? If we, instead of making this public, we make this private, that means that the user can't call it. Only we can call it. Imagine now writing a public function that calls this. So we would, and you overload it to have the exact same name. So we would have a public int tr fact that takes a single value. This is method overloading. They have the same name. You make one of them public that only takes one thing. And since this product is always a consistent 1 the first time that you call it, you can just factor that out into this overloaded call. And now when the user uses your code, they call this, pass what they expect to pass, and you figure out what the constants are and then pass that on to the logic that actually figures out the factorial. So now you have a level of ease of use that you did not have before. The user calls this the way that they expect, and they can't screw it up. Something that you will find as you go into industry, treat your client / user like they're in 2nd grade. And if they can mess something up, they will. In fact, they'll just do it to mess with you, or they'll do it for fun. If you ever work with a 2nd grader and you tell them you can break the rules, their eyes. How? Your programmers are going to do exactly that. If they can break it, they will. So you need to hide the ability to break it behind something that can't be broken. Questions about any of this? The rest of this, I think, says exactly this. We found the annoyance. The solution was to do that. All right, the next big topic I want to talk about is we've talked about recursion, but we haven't talked at all about how to figure out how efficient your recursive solution is. So we need to talk about that. With loops, for the most part, most of your loops go from 1 to the input size. So you're able to just kind of look at the number of loops inside of loops or loops after loops and use that to construct an approximate time complexity for your algorithm. How do we handle recursive calls? How do we figure out the order that recursive calls operate in? You have to use a tool that we're going to call recurrence relations. So we have a recursive function, we need to figure out its complexity. Before we even do this, does anyone have any ideas about how you would figure this out?
Figure out how long it takes to get the base case, maybe.
Okay, figure out how far away is the base case. That's gonna vary. So let's say we're trying to reverse a list. It's gonna take longer to get to the base case if our list is of length 1,000 than it is if it's length 1. We're gonna start in the base case if it's of length 1, and it's gonna take us quite a while to get there if we have a list of length 1,000. How do we represent a mathematical function in terms of the length of the list if we don't have an entire iterative solution in front of us? That is a good point of figuring out how long it's going to take us to get there. That's pretty much correct. But how? How do we do that?
Figuring the runtime complexity and kind of comparing it to ones.
Kind of. Kind of. This is good. It turns out what we're gonna be doing is we need to figure out how many recursive calls do we have? And what is the size of the recursive call compared to the size of the current recursive call? And how much work are we doing in addition to that recursive call? So as we do this, we're going to basically be deriving piece by piece a mathematical expression, which we can then analyze. I think this makes way more sense if we look at some examples. So let's start with factorial. To solve factorial, when we make the recursive call, we're making the recursive call of a factorial that is 1 smaller than the current factorial. So to calculate factorial of 5, we need to calculate factorial of 4. How much extra work are we doing in the function to get factorial of 5 if we had factorial of 4? It's one more thing. Basically, we said that factorial of 5 equals factorial of 4 times 5 is how we decided to do this. This is one operation. Which is where this plus 1 comes from in our expression. So this says the complexity of something of size n is the complexity of something of size n minus 1, and there's one operation that we need to do in order to calculate this from that. The other thing we need to figure out is how complicated is the base case. So how many operations does it take for us to calculate factorial of 1? So the complexity of calculating factorial of 1 is one operation. We return just that one thing. So we could start to expand this. So, of course, I have to erase this. So to solve a problem of size n, solve a problem of size n minus 1, and there's one additional operation that we need to do. So we've represented a variable in terms of a smaller variable, just like we did with factorial, just like we did when we were recursively solving things. We're getting closer and closer to the base case. We want mathematically to get closer and closer to the base case as we analyze this. So now we have defined T of n. How can we define T of n minus 1? Yeah. So in addition to this expression, we could write T of n minus 1 equals T of n minus 2 plus 1. We could write T of n minus 2 equals T of n minus 3 plus 1. We can continue this process as long as we wanted to, basically. how would this expand? How could we back substitute this logic into T of n? Could we represent T of n in terms of T of n minus 3? Yeah, we have the T of n minus 1 here, which is a variable we've defined in terms of T of n minus 2, so we can substitute this right-hand side for that. And then we can substitute this T of n minus 2 for that right-hand side and substitute that back into there. So we end up just doing lots of back substituting and back substituting and back substituting. How many operations do we think it takes to solve T of 5? If you were to solve this all the way out and back substitute, T of 5 would be what?
Back substitution step.
Yeah. So T of 4 plus 1, which is T of 3 plus 1, we would end up with T of 5 equals 1 plus 1 plus 1 plus 1 plus 1. So we will see, and this makes a lot of sense with regards to factorial, that this is linear in nature. Whatever this number happens to be, that's going to exactly be this number here. So this recurrence relation, T of n equals T of n minus 1 plus 1, is a linear recurrence relation. It represents big O of 1, sorry, big O of n. So we can map the math that we're doing, expand it out, back substitute, come up with a mathematical expression, solve that mathematical expression for n. And that will allow us to get some kind of order associated with the math. Does that make sense? It's not the most fun process ever, but in general, this allows us to figure out how complicated a solution is. So we get something like T of n equals n. So tells us that the recursive version of factorial is a linear time recursive function. How about Fibonacci? Go ahead and try this on paper and see if you can come up with something that makes sense. Working groups, see if you can work together and find a solution to this. Perfectly okay if you get stuck. Note that Fibonacci had more than one recursive call. So we can figure out the baseline. I'll give you the baseline. T of n equals T of n minus 1 plus T of n minus 2.
T stands for time.
It's just the symbol that we use. Yeah, it's like the time to have something of input in. It's perfectly fine to run with. I don't even know what it technically stands for. It's just the symbols that are usually used for it. How many operations do we have? It is. We'll see why that is, but yeah, this is an exponential complexity. How many operations did we have to do as we figured out, given t of n minus one and t of n minus two? How many operations did we need? It's still some constant number of operations, so whether this is one or whether this is three, doesn't really matter, but we needed to store something in t of n minus one and t of n minus two, basically the one ago, the two ago, and the current. We needed to store something in each of those, so it's really should probably be something like plus three. But you'll get the same order regardless of what constant you use here. So let's take a look at this. So we've defined t of n and t of n minus one. If we back substitute from t of n minus one, we keep the t of n minus two that was there, but t of n minus one and t of n minus two and t of n minus three, and we added three to this as well when we did that, so this is plus six. We can define t of n minus two as t of n minus three and t of n minus four. We have two t of n minus twos that we need to expand in such a way. So we get 3, 4, the 3 in the middle, 3, 4. We did two expansions that added two additional plus threes. So this is now plus 12. The 6 plus the two expansions that we did that also added plus 3. So t of n minus 3, we can now do in terms of t of n minus 4 and t of n minus 5. So how many t of n minus 3s did we have? 1, 2, 3. So we're going to do 3 expansions. This 3 becomes 4, 5. Move down the 4. This 3 becomes 4, 5. This 3 becomes 4, 5. Bring down the 4. We did 3 more expansions, each of which cost 3. So this has plus 21. As we continue this process and back substitute, we can find that t of 1 was 1. So the other thing we should talk about is the base case, t of 1. We can figure out in constant time that the first Fibonacci number is constant time. We can figure out as 1, we just know it, so we can substitute it. So this number here is going to be growing exponentially as we add more and more and more and more substitutions. Because now we have 1, 2, 3, 4, 5 t of n minus 4s that we would need to expand. Each of them would add an n minus 5 in addition to the n minus 5s that are here already, creating more and more n minus 6s, more and more and more and more n minus 7s. Does that make sense? This is why this is exponential. This is growing at an exponential rate. And the number of terms is growing at an exponential rate. So, explosion of complexity. Remember when we had our iterative Fibonacci and our recursive Fibonacci, and as we did more and more work, it started to become painfully obvious that the recursive version was slower than the iterative version. If we analyze this, we can figure out exactly why that is. The iterative version is not doing this explosion of complexity. It's always finding term one and term two. Use that to find term three. 2 and 3 was used to find 4. 3 and 4 was used to find 5. There was never this explosion of complexity where we were solving the same problem over and over and over and over again. So that's the reason the recursive version was taking so long. All right, enough of me talking. We have a little bit of time. Let's start with the next recursive problem that I will have you working on. So in homework 2, I asked you to basically analyze the complexity of binary search. If you recall, we were trying to find a needle in a haystack, finding a value in an integer array. So the basic idea of what we want to do is to check the value in the middle of the list. If that is the value we are looking for, return it, return the index, the middle of the list. If it's smaller than the middle element, because we know that the haystack is sorted, we will repeat this logic, only looking at the first half of the array. If it's larger than the middle element, we want to repeat this logic, only looking at the latter half of the array. So go ahead and pair program this, implement it recursively, not iteratively. So I think we can probably spend the rest of the class on this, since this is gonna take a little while. But find somebody to work with and see if you can crank it out. Alright, so. We do need to check the. A lot of individual work. This is good that everyone is being very successful. If it is not being very successful, introduce yourself to your neighbor and see if you combined can figure it out.
It is. Yeah, so I mean, this is, the endpoint. Then you like, showing up the next, like, and it goes to this, and it runs the base case, so. I go to the next, like. And then. It checks. The value that it's put in, and it like. And then if not, it adds it, so it's like. Starts in the middle, and then it either goes to the side or the other side. And then that becomes. And then it calls itself again. Until it. So they're on your, like, where it's at.
That's why I was thinking. So I was like, it's the hell. That's why.
Maybe you need to sort out the text into the next. So I mean, you could also just. That's good. I think that be able to tell next business where it was. Yes, or so. So it's like when I pass it through here, it just says it as the middle. Pretty sure I tested it and it was here that I these were the values.
The whole thing. I know, we get the middle, yeah, but then, so we get the middle, so, yeah, and then.
Which would be that sound that.
That was very calm.
Exciting as this has been. We are out of time. My challenge to all of you is to finish this off between today and tomorrow, and we will program this live tomorrow. The more of you have finished it off, the more helpful you will be as we write this together. See you tomorrow for that. Office hours starting now, starting on the license with homework, everything else. I'm working around.